Hello and welcome to this EE328 lecture video on discrete-time system stability. So we're going to cover the two main flavors of system stability that one can use when talking about discrete-time systems. And we're going to, because we have some tools in our tool belt now, we can now more easily talk about how to classify a system as stable or unstable. So the first sub-flavor of stability that I want to talk about is called external stability. And the definition of an externally stable system is one that always produces a bounded output if presented a bounded input. And the one caveat to that statement is that we're talking about zero state outputs. So the output of this relaxed system is going to be bounded provided that the input was bounded. And because of that phrasing, it's a little bit awkward. It's often called BIBO, or bounded input, bounded output stability. And so we have a tool now to talk about the ZSR of a system due to an arbitrary input, and that is the convolution with the impulse response. So if I have an LTI system whose impulse response is h of n, and I excite this with the signal x of n, then the ZSR, we know, is the linear convolution of x with h. So this looks like k running from minus infinity to infinity of, say, h of k, x of n minus k. And so I'm going to impose one more assumption here, and that is we have to assume this input signal is bounded. Now, a bounded signal, recall, is one that has a max and a min. So this is equivalent to saying there exists a finite number m such that absolute value of x at any time is less than or equal to m for all little n. Okay, so basically there is a floor and a ceiling around the input that the input never crosses or never goes beyond. Okay, so our job is to ascertain what restrictions on the impulse response make the output bounded if we assume the input is bounded. So let's work that out. Okay, well then to ascertain whether the output is bounded, we actually don't want to talk about the output, we want to talk about the absolute value of the output. Right? Because if we can show that the absolute value of the output is less than a fixed number, then that is the definition of being bounded. So if I take the absolute value of the left, I'll take the absolute value of the right. Over all k's. And so the absolute value of this sum has to be less than or equal to if we were to add up only positive things. So h of k times x of n minus k. Right, if I take the absolute value after I add, then there is the possibility of cancellation, pluses and minuses, and so we can get a smaller sum than if we were just adding strictly positive things, which is what we have here on the right-hand side of the inequality. Okay, so again, what I'm trying to do is I'm trying to find a bound on the absolute value of the output at any given time. And the absolute value of a product is, it won't surprise you, the product of absolute values. So this actually equals the sum of the absolute value of h of k times absolute value of x of n minus k. Now here's where we're going to use the assumption on bounded input. If x is bounded at every given point in time, then a shifted and flipped version of x will also be bounded by that same number. Right? These operations are all kind of, if you like, left-right operations. They're not up and down operations if I'm thinking about the graph of x versus time. And so my claim is that this thing is always less than or equal to that bound we had on the input. Okay, and that was by assumption. So if this thing is less than or equal to m, then the entire sum is less than or equal to, if I replace each of them by m, and I get the sum of the absolute value of h of k. K running over all the integers. And so here's where we get to the crux of the matter, is that if this is finite, then I get a finite number times a finite number, and that shows that YZSR at any given time is always bounded. And so that's where we get this conclusion, is that if this is true, and we call that condition absolutely summable, if H is absolutely summable, that is, the sum of its absolute values is a finite number, then the system is Bibo stable. Now, what I have here on the slide is actually a bit stronger of a statement, and it goes the other way, is it says if the system is Bibo stable, then H must be absolutely summable. We won't cover that exact proof. It's interesting, but it's not quite something that you need to know at this point. But what you should know is that if H of n is absolutely summable, then the system whose impulse response it is Bibo stable. The other kind of stability that is relevant to talk about deals with ZIRs, right? So externally stable means if you only feed a system bounded inputs, you are guaranteed bounded ZSRs. The other kind of stability, which we call internal stability, is a condition on the ZIRs. And so what an internally stable system says is that any set of initial conditions produce a ZIR that tends towards 0. Now, if you have a finite impulse response, then you get internal stability for free. And you get external stability for free as well, because if you have a finite set of numbers, that has to be absolutely summable, provided all those numbers are finite themselves. But so this is mostly kind of an interesting result when we talk about infinite impulse responses. So let's see exactly what's going on here. If I have a ZIR, so Y ZIR of n, that will, in general, if I have an IIR type system, be the sum of the characteristic modes. So this is Ri to the n, I running from 1 to capital N, the order of the system. So remember, these were constants or residues, and these were characteristic roots, and that when I raise them to the n, they become characteristic modes. And so what it would take for, and these constants are determined by the initial conditions. And so if I want a statement to hold for all possible initial conditions, I can't condition the statement on the constants, which means that's why we're going to focus on this part and not really this part. So if I need this signal to tend towards 0 as n goes to infinity, so I need y ZIR of n as n goes to infinity to tend towards 0 if I want the system to be internally stable for all possible initial conditions. And the way that I can guarantee that is that if each of the characteristic roots, when I raise them to higher and higher powers, gets smaller. Because I'm adding these up, I can't count on cancellation, so what I have to do is I have to enforce that each of the roots has to get smaller if I raise it to higher and higher power. And the only way to do that is to make sure that the root has a magnitude less than 1. So this is where we come to the unit circle in the complex plane. So we'll plot the real part of the roots. Here, let's use R here, and the imaginary part of the roots. And so this is significantly different than in continuous time, because in continuous time, if you had a root of your characteristic equation over here on the right half plane, anywhere in the right half plane, that would correspond to a continuous time exponential that increased with time. But what we've got now, and we're going to call these poles or characteristic roots, same thing. If you have a characteristic root inside the unit circle, so this is the circle that runs from 1 to j to -1 to -j, then this is a fraction, right? This x represents a fraction. It happens to be a positive fraction, but if I raise a fraction to a higher and higher power, then I get a smaller and smaller number. same thing as if I had a negative fraction. It's going to oscillate, right? It's going to go negative, positive, but those in magnitude, they're going to tend towards zero. It's going to bounce above and below the axis, but they're both going to converge towards zero. If I have, say, roots on the imaginary axis, then that corresponds with sines and cosines, but they have a magnitude out in front that is going to be damping them over time. So again, these two x's, these two poles, will lead to oscillatory modes, but they're going to lead to damped oscillatory modes. So these are going to be things like 1/2 to the n times cosine of n pi over 2. Right? This part continues to bounce around, but this part gets smaller and smaller. And because I'm multiplying them, that overall, the product of those two gets smaller and smaller. And so that same result happens provided we are anywhere inside the unit circle. Right? You get oscillations, possibly, but as long as the magnitude of these roots is less than 1 strictly, so note the strictly here, then you get a ZIR that tends to 0. In the edge cases are when we're on the unit circle. So this red would correspond to a mode that looked like 1 to the n. And so this is, in some sense, just fine. This does not grow without bound over time, but it's not as nice as it could be because it doesn't decay over time either. In particular, I think this would make most engineers nervous, because what if you got it a little wrong? What if it was actually over here and it was like 1.01 to the n? Well, then it would take a while, but sure enough, it would eventually grow without bound. Okay. So when you have roots on the unit circle, we call those marginally stable systems. And when you have any roots of the characteristic equation outside of the unit circle, these correspond to internally unstable systems. That was it. It's a quick lecture on stability, which is a new kind of system class that you can put your systems into. Thanks for watching.